Hello everyone and welcome to Calculus 1. This is the start of our Calculus 1 course where we're just going to go over and talk about calculus and work through some problems. The way that I will be formatting these videos is that I will have videos that are just based on the content with maybe one or two practice problems, and then a additional video that will go over purely practice problems so that we can spend the time focusing on the content and then take that content knowledge into practice problems in a separate video. So today we're going over the limit. We've got an introduction to the limit, which is an introduction to calculus as a whole. To start, we're going to look at some ancient paradoxes that were discussed in ancient Greece by Zeno. Some of these are also known as Zeno's paradoxes. So the first one here is the dichotomy. The dichotomy is saying that if you've got a runner, someone here who's racing to a finish line, then we can think of this runner as taking steps between his race, right? He starts at the beginning, and at some point he's going to be halfway through the race. And once he's halfway through the race, then he's going to continue running, and he will reach another point again where he is halfway between where he was, halfway between this point 1 and point 2. And once he's at point 2, he's again going to keep running, and he's going to become halfway between his starting point at 2 and the finish line. So now he's at 3. Once again, he's still running, and there becomes a point where he reaches halfway through the mark. And again, halfway, and halfway, and halfway. It keeps getting closer and closer to the finish line, but does he ever reach the end? If every time he's getting halfway closer, halfway closer, halfway closer, he's never going to reach the end, because there's always going to be halfway more that he can run. After 5, he's going to go halfway between 5 and the finish line. That's going to be 6, halfway between that, 7. And we can keep zooming in onto this spot here, and it's just going to look like this whole thing again, where over here is 5, this is 6, 7, 8, 9. No matter how far that he runs, he keeps getting closer and closer, but never actually reaches the end because he just keeps going in halfway intervals. But if you've ever ran a race or seen a race, you know that this guy, he will cross the finish line at some point. He does go past that mark, and he goes past the finish line. He finishes the race. But how does that happen if every step he takes, he's only going halfway as far as he was? How is it possible? Similarly, we have this arrow paradox, where we have someone who's shooting an arrow through the air, and if you take a camera, you see someone who shoots an arrow, and you're taking pictures at different times. Here we've got 5 different pictures that we've taken of this arrow being shot from the bow. And in each picture, this arrow is just frozen in time. It's not moving. It has no velocity. It is just an arrow in the picture, in the sky. You can't determine anything. You can't determine where it is or where it's going, or that it was ever moving, because in these pictures, they're all stationary. They're not moving in the picture. So if we look at every single interval, if we look at each of these dots and think of them as a picture that we've taken, then how does it actually move? How does the arrow move if each of these pictures, each moment in time that we're looking at this arrow, it's not moving, it has no velocity? How does it actually get shot, and how does it actually move and fly through the sky to land? How does that actually work? Well, both of these, and there are many other examples of Zeno's paradoxes or other paradoxes of time and movement like this, these really all talk about what is calculus at its core. How do we actually think about things when they're so infinitely small, right? If we're looking at this infinitely many times, right, we'll have infinite number of pictures of this arrow where it's not moving. Or we have infinite number of time intervals where this man running is only halfway from where he was to where he's going. We're looking at the infinite number of ways that we can get from one spot to another, but at each moment in that infinite, nothing's actually happening. We're not making progress. We're not moving. And that is calculus at its core. It's what's happening if we look at something with infinity in mind. And infinity is just such a weird concept that is hard to think about for the first time. And that's what we're going to start looking at in this course. So the first thing that we're looking at is the limit. That's what this whole video is called, is Introduction to the Limit. So let's think about what the limit actually means. And the limit is taking that infinity concept and trying to break it down. So here we've got a graph a graph of y equals 1 over x. We're looking at the positive side. There would be a negative side as well. But for y equals 1 over x in the positive side, right? If we look at this graph, we can see that it starts with the y very high and it quickly tapers off and goes down. And if we're looking at half, 0.5, our y is at 2. This is 2. If we look at 1, then our point is at 1. If we look at 2, we're at a half. If we look at 10, we're at 0.1. If we're looking at 1,000, we're at 0.001. And if we keep going, this would be what? 100,000 here? If we keep going, it's getting closer and closer to 0, right? These are very small numbers. And if we keep going down this line of this table, we go down to 1 million, 100 million, 1 billion, 1 trillion, right? It's just going to keep following this pattern. We're going to go all the way out. And this number keeps getting smaller and smaller and smaller. But does it ever reach 0? That's what we're looking at, right? It looks like, right, we're getting super close. This number is so close to 0 here. But does this ever actually reach 0? And that's what we're looking at with limits. If we look at it with a discrete number, no, it's never going to equal 0. It's going to equal something like this. But if we look at it with a limit, then there's a point that if we think about this going on to infinity, and remember, infinity is not a number, it is a concept. If we think about this as the concept of going out to infinity, x equals infinity, then we will hit 0. This will equal 0, but it's the limit. It's not the actual number, and those are different. So what is a limit? Well, this is what a limit looks like. We have the limit here as x approaches a number a. In our last example, we were looking at as x approaches infinity. If a is equal to infinity of a function, then that equals L. So for our last problem, right, we had y is equal to 1 over x, and we would write this as the limit as x approaches infinity, right, because we were going on this and looking at as this goes towards infinity, as x goes to infinity of f of x, 1 over x, then this is going to equal 0. And we're going to look at these special types of limits in another video, but that is generally how these limits are set up, right? So we've got the limit as x approaches a number, and here we were looking at infinity. As x approaches a number of the function f of x, then that equals L. So this is the limit of f of x is equal to L as x approaches a, given that the limit from both sides of a is L. Okay, so this is something that we're going to have to look at a little bit more. Given that the limit from both sides of a is L, what does that mean? Well, we'll take a look at that. So here we've got an example of a limit. We're looking at the limit as x approaches 4 of x squared minus x minus 12 all divided by x minus 4. If we go ahead and just plug in the number, if we say, okay, well, what does this equal if we just put 4 in? Well, we put 4 in, we get 4 squared minus 4 minus 12 all over 4 minus 4. We solve this, we get 16 minus 16 over 4 minus 4, which is equal to 0 over 0. That's a big red flag. Not only we are dividing something by 0, but we're dividing 0 by 0. That's really weird. So f of 4 does not exist. And what does this look like? Well, this looks like this line here, right? This line with this point of discontinuity at 4. If we look at this function going from the left-handed side, right? So if we're looking at the point 4, let's approach this from the left, right? If we go from the left here, going up this side from the left of 4, what do we equal? Well, let's plug in some numbers that are to the left of 4 and see what we get. If we choose the point 3 here, we plug it in, we get 6. If we choose 3.5, we get the point 6.5. If we choose 3.9, now we're getting closer and closer to 4, right? 3.9, we get 6.9. If we go even closer to 4 from the left, right, slightly below 4, we get 3.999, and that is equal to 6.999. If we look on the other side from the right, so we start up here and we go down to approach 4. We're going down to reach 4 from the right, so slightly larger than 4. If we look at 5, we get 8. 4.5 is 7.5. 4.1, 7.1. And 4.001 is 7.001. So if we look at these, right, on the left, it looks like we're starting lower and we're getting closer and closer to 7. Like 6.999 is very close to 7. Whereas on the right, we're starting higher And we're going lower. We're going from 8 to 7.001. That's also very close to 7. And if we plug in even closer numbers, right, if we choose 4.0000001, we're going to get 7.0000001. So it's going to get closer and closer to 7 at the point 4. Similarly, from the left, this is getting closer and closer from the left, from the lower number, to 7. And so I can say that from the left, the limit as x approaches 4, with this little minus sign there, that minus sign in the superscript of 4, that means from the left. So the limit as x approaches 4 from the left of f of x is equal to 7, because you can see we're getting very close to 7. We're never hitting it, but we're very close. And same thing from the right, we've got the limit as x approaches 4 from the positive side being from the right, then that's also going to equal 7. And since we've got the limit from both sides, from the left side equals 7 and the right side is equal to 7, then we can say that the limit of f of x as x approaches 4 is equal to 7, because both sides from the left and from the right both equal 7. So let's look at this a little bit closer. If we look at this graph here, we've got some lines here with some discontinuities. So let's go ahead and just try and fill out this table. So we've got a here. Let's look at a is equal to -3. So we've got -1, 2, 3 is right here. We're looking at what f of x equals at -3. Well, we've got this open circle here, which means it is not equal at this point. But we've got a closed circle up here, which means we are equal at that point. So -3 is going to equal this point here, which is 2. Alright, so as the limit as x approaches -3 from the negative side, right? So I'm going to rewrite this just so we can look what it's going to look like. This would be the limit as x approaches -3 from the left of f of x, where this blue line is f of x, right? As we approach -3 from the left, from the negative side, right? I'm going to look at what we've got. Well, we've got this blue line here from the left. As we go from the left, well, this is approaching, it's getting closer and closer and closer to the point y equals 2. Whereas we look at it from the right, so if we look at the limit as x approaches -3 from the positive side from the right, well, we find our graph and we trace along the graph until we get to where we're looking. On the right, well, we stop at this point, but it's an open circle. And it doesn't equal that, but that's okay. It doesn't have to equal at that point. We're looking at what it's getting closer and closer to. And if we look at our last example, right, it didn't exist here. We just got really close to that point. So if we look from the right here, although we don't ever hit this number, we get closer and closer to it from the right. So that's -1. And now if we look at our total limit, the limit as x approaches -3, well, do our left and right hand sides equal each other? Well, no, we've got 2 and -1, so those are not equal, so this does not exist. Alright, let's look at 0. So if we look at 0, f of x of 0, well, this is an open circle here, so this does not exist. There is no other point here. There's no jump discontinuity or remove discontinuity. There's no discontinuity here that we can actually place the number at. It is just a hole, right? So that does not exist. If we look at it coming from the left-hand side, so we find our graph, we trace along from the left-hand side, and we get -3. Although it's not equal to like -3, it approaches. It's getting closer and closer to that number, but not equaling it. Same thing from the right, from the positive side. So we go and we trace our graph, and we get, again, -3. Now, since our left and right-handed limits are equal, then we can say that the total limit as x approaches 0 is -3. Okay. For number 2 here, f of x, if we look at 2, then we've got this point right here, which is at 2. That's what our point is, but we do have this discontinuity here. So f of x is 2 at that point, but if we look at from the left-hand side, let's go ahead and trace. We get 1, 2, 3, 4. We get the limit from the left is going to equal 4. And from the right-hand side, again, we're going to trace along our graph, and we get 4 again. Since these two are the same, we're going to get our limit is 4. And finally, looking at x equals 4, f of x, well, we've got a filled in hole here, so that means that our point does exist at that point, and that is 1. If we look at from the left, we get, trace it, and we get 1. And from the right, once again, we'll trace our line, and we get 1 again. And so our limit, since both of our left and right hand sides are the same, then our limit is also going to equal 1. So just as a review of our limits, we're looking at dealing with infinity. This is our first time ever really looking at infinity and trying to work with it and understand how limits work and how calculus works with the idea of infinity in our mind. Limits look at functions as we approach values from infinitely small intervals. So that's looking at right here, if we looked at 3.999, that's infinitely small, infinitely closer to the point that we're looking at, but never actually reaching that point. We're looking at the functions as we approach from infinitely small intervals. Remember that if we're looking for the limit of the entire function, the limit as x approaches a of f of x, that equals L if the left-handed limit from the negative side and the right-handed side from the positive are both equal to L. If these are both equal to each other at L, then our limit is equal to L. And if we look back here, right, we had our example here in pink where our left-handed and right-handed limits do not equal each other. We had one that's equal to 2, and then the other is negative 1. So the limit does not exist. But in these 3 other examples, right, our left and right-handed limits are equal to each other, and so our limit is equal to that point. We've got that if f of a does not exist, that doesn't matter. We can still have a limit if f of a does not exist, right? And we saw that here. At this point in red, f of x, f of 0 does not exist, but the limit is still negative 3. The limit still exists, because we don't care if it actually exists there or not. We're looking at what it's approaching as we reach infinitely small intervals to this point, as we get infinitely close to that point, but not what it actually is at that point. So f of a does not need to exist. And finally, we can find the left and right-handed limits by plugging in numbers close to a, and that's what we've been doing to look at these infinitely small intervals as we get closer and closer to that number. So that was our introduction to the limit. We are going to continue with some more limits in the next video, and I hope you stick around for it. We're going to go through some practice problems as well for limits as a whole in a future video. So thank you so much for watching, and I will see you next time.